Okay, this is section 6.1, the nature of light. So as we start looking at the second part of this course, we're going to start looking at the structure of matter in more detail. The beginning of this discussion has to do with what are called electromagnetic waves. And electromagnetic waves make up what's called the electromagnetic spectrum. Now we are sensitive, aware of, perceive certain types of electromagnetic waves due to evolution and natural selection. We're very sensitive to visible light. We can see different colors of light. We can see the differences between green and blue. We are also sensitive to infrared magnetic waves, electromagnetic waves. Sometimes we perceive it as a transfer of heat. We're not, on the other hand, all that sensitive to being able to perceive X-rays or gamma rays or radio waves. We need technology to be able to detect and measure these types of electromagnetic waves. Okay? So this is an issue of the nature of light. We're going to use the word light as a colloquial term to mean electromagnetic waves. So let's begin by reviewing the electromagnetic spectrum. These are all the different types of electromagnetic waves that have been discovered over the years. Perhaps you've heard of gamma rays. Gamma rays are a type of electromagnetic wave that is emitted by certain types of stellar phenomena such as supernova or black holes, things like that. There are also some types of radioactive materials that produce gamma rays. There are also what are called X-rays. X-rays we're familiar with in terms of imaging. X-rays are high energy particles, high energy waves that can penetrate through soft tissue but get reflected off of and absorbed by more dense elements. So bones, for example, will reflect them as opposed to allowing them to pass through. So that gives us a contrast, and we can use that for X-ray imaging. There are ultraviolet waves. Ultraviolet radiation sometimes is called UV rays. We know of them because they actually cause sunburns and even cancer. At the same time, they're necessary for vitamin D production in the body. So those are UV. Then there's visible light. Those are the types of electromagnetic waves we're most familiar with. All of the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. Roy G. Biv, sometimes that's called. Then there's infrared. Sometimes we have little sensors that can detect infrared radiation. Microwaves, which are used for communications and also used for cooking food, right? And then there's radio waves. So these are all different parts of the electromagnetic spectrum. They are all different types of waves. You'll notice on this figure that there are two rows with numbers. The first one is wavelength, and then in parentheses it says NM, and then below that is frequency, and in parentheses Hz. Okay, so there's a pattern. Now these are these are powers of 10 that we're looking at. This is a logarithmic scale for both of them. So 10 to the minus 3 for wavelength on the far left to 10 to the minus 1, that's gamma rays and going into X-rays. X-rays going into ultraviolet is 10 to the minus 1 to 10. That would be 10 to the plus 1. And then from ultraviolet to visible light is 10 to 10 to the 3, and so forth and so on. So those are powers of 10. So we're talking about an enormous range, 10 to the minus 3 nanometers, nm, all the way up to 10 to the 13th. And then notice there's a reverse pattern with the frequency. The frequency starts off at a very large number, 10 to the 20th for gamma rays, but then becomes much smaller as you move to the right all the way over to radio waves where it's only 10 to the 4. So there's an inverse relationship between the two. As wavelength gets larger to the right, frequency gets smaller to the right, so they're inversely related to each other. You may also notice that in the visible light, there are different colors indicated with numbers as well. Those are wavelengths, okay? They're showing you the wavelengths in nanometers. 400 for violet, 450 or so for blue. By the time you get up to 500, it's starting to turn into a little bit greenish. By 550, it's definitely green. By 600, it's orangish yellow. And then 650 to 700 starts turning red. So each of the colors of light that we're sensitive to corresponds to a specific range of wavelengths in nanometers that are indicated here. It would also frequency as well. It's just not shown there on that scale. Okay. Now let's talk about the primary characteristics of waves that we would be interested in here today. And that is the idea that we're going to measure, or we're going to consider, wavelength, frequency, and speed. Okay? So wavelength is, let me show you a depiction here of a wave. A wave, I'm not showing this very well, is a repeating oscillation, a repeating pattern. Okay, so notice the height of the wave is increasing, leveling off, and then decreasing. And then it's leveling off, increasing, leveling off, decreasing, leveling off, increasing, leveling off, decreasing, leveling off, and then increasing again. So it's a repeating pattern, right? So imagine that horizontally, this is distance. Or if you want to use the term length. Okay, now what are the units of distance or length? They could be meters or centimeters or inches or feet or miles. There's all sorts of units that we could use. Typically, we use either meters or nanometers for this course. Okay, I'm not claiming those are the only units that are used. If you take other courses, you'll use other units, but those are typically the units of length or distance that we're going to talk about in terms of the electromagnetic spectrum. So we're going to define something called the wavelength as the distance on the horizontal axis, the x-axis we call that, the distance between two adjacent peaks. And the symbol is a lambda. Let me spell that letter out. It's a Greek letter. Lambda. So lambda, the wavelength, is the distance between two adjacent peaks, between the two peaks right next to each other. Okay? Now, we're making an assumption here, and the assumption is that it would be the same distance to here as well. From here to here would be the same distance. Okay? That's called the wavelength. It's a measure of how long the wave is. Okay, so if we come back and I show you two waves, so here's one, here's wave 1, and then here's wave 2. One of these two waves has a shorter wavelength, the other one has a longer wavelength. Which one do you think is shorter, and which one do you think is longer? This one's shorter, right? The distance between those two adjacent peaks is shorter. Okay, now I haven't even shown you the complete wave. Let's go from here to here. The distance there is longer. So this is a longer wavelength. Okay? So some waves are long, some waves are short, as we saw in the electromagnetic spectrum. Some of them have very short wavelengths, other ones have very long. The radio waves have the longest wavelengths, and gamma rays have the shortest wavelengths. So that's one quantity that we talk about in terms of the properties of waves, is their wavelengths. Another property is the frequency. So let's talk a little bit about frequency. I'm going to pronounce that letter, that symbol. It looks like a V, right? It looks like a cursive V, a script V. It's actually nu. It's also a Greek letter. And that is often used for frequency. Sometimes a lowercase f is used. And that's perfectly fine if you want to use f for frequency. Okay? Many physics books use f. So again, now I'm going to draw the wave. Again, I'm trying to draw this as pretty as I can. Here we go. Okay. Now we're going to consider on the x-axis time. So imagine that you've got this repeating pattern. Look out on the ocean. You see the water coming towards you. It comes to, there's going to be a peak, and then it's going to get lower, and then it's going to peak again. The waves are crashing onto the beach towards you in time, right? They come in time. In some sort of repeating pattern. So what I'm going to do is I'm going to call the distance on the x-axis here, it's a time unit, right? I'm going to call that the period of the wave. And that's typically a T, capital T for period. Okay? So that's how long it takes from the point of one wave reaching you to the next peak reaching you, right? So if one peak reaches you right now and then a second later the next peak comes, that would be a period of 1 second. But another way of thinking about it is the reciprocal, not thinking of how long does it take for one complete cycle, right? Because that's really what that period is. It's the time of one complete cycle, how long that takes. Another way of thinking about it is how many cycles will come through a certain point in a given period of time. And just arbitrarily we'll say that that period of time is 1 second. We don't have to do it in 1 second, but we will. So in 1 second, how many peaks will come through a certain point? So again, imagine they're moving to the right. This wave is moving to the right. And let's say in 1 second, your eyeball is right there. So you're looking. And let's say this peak comes through, this peak comes through. That's one complete cycle, right? Another peak comes through, so now we're up to 2 cycles. Another peak, so now we're up to 3 cycles. So let's say all 3 of these cycles reach your eye in 1 second. We could think of something which is called the frequency, which is the number of cycles that pass through a point in a given amount of time, which we'll say is a second, in 1 second. Okay? If it was 3, we would say that it's 3 cycles per second. How many cycles per 1 second? 3 cycles per second. And we're going to call a cycle per second. We're going to call that a hertz, named after Helmholtz Hertz. Helmholtz Hertz. And so let me write that as HC, 1 hertz. Okay? So that's the unit of the frequency. Okay, now it turns out the frequency is equal to 1 over the period. Because if it takes 0.33 seconds, a third of a second, for one cycle to come through, then you would get 3 cycles every second. You'd have a frequency of 3 hertz. So they're reciprocals of each other. We're not going to worry about periods. That's something that you might worry about in a physics course. We are only concerned with frequency in this particular subject matter. Okay? So we now have 2 quantities. One is the wavelength, and the other one is the frequency. Now I'm going to connect the two. I'm going to make the following claim that the wavelength, I'll write these out for now, but in a moment I'll write the equation. The wavelength times the frequency is equal to the speed of the wave. Remember, this wave is moving. Okay? Wavelength times frequency. So the symbol would be lambda for wavelength times frequency nu is equal to the speed. And I'm going to use the symbol c. When we talk about the speed of a wave, we often use the symbol c, lowercase c. If we're talking about a molecule moving, like when we dealt with gases, we'll use a u. But for waves, we'll use a c. Okay? So wavelength times frequency equals the speed. Now, we are talking about electromagnetic waves in this topic. We're not talking about sound waves. We're not talking about earthquakes. We're not talking about any kind of waves except electromagnetic waves. Now, electromagnetic waves, interestingly enough, it doesn't matter what their frequency is, doesn't matter what their wavelength are. They all move at the same speed if they're in a vacuum. So in a vacuum, the speed of any electromagnetic wave is called the speed of light. Now, this is not true if they're not in a vacuum. Waves will slow down if they have to pass through matter. But in a vacuum, all types of electromagnetic waves move at what is called the speed of light. And the speed of light has been measured and measured and measured and measured for 100 years to great precision. It's so well known that it's actually now just been pegged at a specific value. I'm just going to put 4 sig figs here, but there are more, but that's fine. And there's your speed right there. The speed of light, the speed of any electromagnetic wave in a vacuum, is 2.997 times 10 to the 8th meters per second. That is a constant. Okay, that's important to note, that this is a constant. Now, I'm also going to point out that the speed of light in an air, or in air, is essentially the same as a vacuum. So we don't have to worry about what the speed of light is in air. We'll just use the same value that we would use in a vacuum, 2.997 times 10 to the 8th meters per second. By the way, for most purposes, it's okay to round this to 3 times 10 to the 8th. If you're doing ALEKS problems, it's going to really cause problems. You want to use the value that they give you in there. But for most calculations in your textbook, for example, 3.0 times 10 to the 8th meters per second is okay. Now, to put that in perspective, that's approximately, so this value, 3 times 10 to the 8th meters per second, is approximately equal to 186,000 miles per second. Not per hour, but per second, 186,000 miles per second. So at the equator, that means that if you were to release electromagnetic waves and they were able to circle the Earth at the surface of the Earth, the circumference of the Earth at the equator is 25,000 miles approximately. So that means that the electromagnetic waves would circle the Earth more than 7 times, essentially 7.5 times every second. That's how fast they move. So the speed of light is a very large number. But it is a constant. So that means that the wavelength of electromagnetic waves times the frequency is equal to this, again, to this number, times 10 to the 8th meters per second. Okay? That's the speed of light right there. So that's an important relationship. It's one that you'll practice in the practice problems, in the sample problems, as you work through this material. Okay? Now let's talk just briefly a little bit more about electromagnetic waves. So here are 2 issues that come up. The first one is, what is an electromagnetic wave? And that's not an easy thing to answer. There's no simple, easy answer that's correct. But imagine that you could measure the electric properties and the magnetic properties of light. So you know what a magnet is, and you know what electricity is. It turns out that light, the material that we see with our eyes, the sun is producing it all the time, is made up of particles, which we'll talk more in the next section, that produce electric fields. Okay, so if you take a charge, let's say a positive charge, a little particle has a positive charge, it will produce an electric field. Around it. And the electric field has the potential to apply a force to another charged particle if that charged particle is within the electric field. So electromagnetic waves they produce electric fields. But these electric fields oscillate, they change in their direction and intensity at the frequency of the electromagnetic wave. So if I say that an electromagnetic wave has a frequency of, let's say, 3 million hertz, that means that the electric field is oscillating at 3 million hertz. But it also produces a magnetic field. So, you know, magnets also produce fields, but they produce magnetic fields. Okay? So electromagnetic waves also produce magnetic fields that oscillate, that change direction and intensity at the frequency of the wave. So again, if this electromagnetic wave has a frequency of 3 million hertz, its magnetic field would be changing at 3 million hertz, 3 million times per second. And the 2 fields, the electric field and the magnetic field, are perpendicular to each other. So this picture here, this little description here, this diagram, shows you in red the electric field oscillating, going up and down, up and down. The magnetic field in blue going up and down, up and down. But notice they're perpendicular to each other. So they oscillate perpendicular to one another. And then the electromagnetic wave propagates, meaning it moves in the x direction. So it's in the y direction, the magnetic field is oscillating. In the red z direction, the electric field is oscillating. And then perpendicular to that in the x direction, the electromagnetic wave is moving. Okay, propagating is the term. Okay, so that's enough about what an electromagnetic wave is. An important experiment studying, for us this is important, is called the double slit experiment. So imagine that we are producing with a light bulb. Okay, so imagine you got this light bulb, like an old-fashioned screw-in light bulb, and it's producing light. It's glowing, light's coming out of it. It could be an LED, could be an incandescent, fluorescent lamp. It's producing light. And now we're going to depict the light with these wavefronts. So the wave fronts are representing the waves as they're moving in a particular direction. So these waves are moving from the left to the right. So this is the direction of propagation. What we do is we take, it's really quite an ingenious experiment. You take a screen that has a tiny little hole in it. And that little hole is S0. You can see it there on the left, the first screen. What that will do is it will essentially localize the waves. It'll make the waves now be at a single point, right? So instead of being spread out over a large region, where is the wave, we can now say that the wave has been localized to a real, to a dot, right? To a single point. But what happens with waves is very interesting. Once those waves come out of that little hole, they start spreading out. And they start spreading out over space. So notice to the right of the first screen, the waves are now spreading out. Now imagine if you drop a rock on a really still surface of water. What happens when you do that? You can see the rock hits the water, and now waves will start propagating as little circles, right? Little circles out from the source of the disturbance. Energy is being transferred out. That rock hits the surface, transfers energy into the water, and then the energy is dispersed through the propagation of waves on the surface of the water. Okay? Now what we do is we take a second screen, and there's two slits there, S1 and S2. And if you take a look at it, the waves are able to spread out through both of those little slits, they're called, those little holes, those little pinholes. Now we've separated, we've broken the waves up into two different pieces. One wave is coming through S1, and the other wave is coming through S2. And notice what happens. This is the phenomenon of the double slit experiment. What happens is something called interference. And interference is something that we observe with waves. Oops, I'm sorry, I misspelled it. This is a wave property. Okay, we don't observe it with baseballs or cars. What happens is these waves interfere with each other. If you take two waves and you superimpose them, and their peaks are at the same space at the same time, you get what's called constructive interference. So what happens is they just add and the wave gets larger. It's kind of cool. So it'd be almost like this. Imagine two people took a baseball, each had a baseball, and threw them, and they happened to hit the same spot at the same time. They would merge together into one larger baseball. That's essentially what waves are capable of doing. It's called constructive interference. However, there's also something called destructive interference. So imagine the first wave is doing this, but the second wave is what's called out of phase, meaning it goes down when the first one goes up and then goes up when the second one goes down. They're completely out of phase. Now you get something that's called destructive interference. And what happens is they cancel each other. There's no wave at all. It disappears. So one wave can actually cancel another wave. So that's called destructive interference. So the double slit experiment, what happens here is you're going to see over here some points where it's bright. Where it's bright, that's photographic film, if you know what a photograph is. Photographic film will show bright spots where you're getting constructive interference. And you'll see dark spots where you have destructive interference. Let's do it this way. Okay. So destructive interference are the dark spots. constructive interference are the bright spots. So what this tells us is that waves are capable of interfering with each other in such a way as to give us bright and dark spots here. This is called the double slit experiment. And this is a phenomenon of waves. Now pay attention to this because later on we will talk about electrons. And electrons we typically think of as particles. However, they are connected to this double slit experiment as well.